Aaron asked me to do a seminar here about a statistical analysis, which actually I have never been giving a talk like this. That's why today's is a very atypical research seminar on my own. But indeed, actually, I want to actually first mention a few examples of my research and just give an idea to see who I am. And but most importantly, I'll kind of like go over some very simple things to touch a little bit actually things about statistics and data and models. So I mean, I don't know you, and probably don't know me either. So I don't know your background. So frankly speaking, I don't really know the audience here. But surprisingly, today I found my two students there, and so that's a big surprise. So I mean, so myself and I do actually do a lot of geospatial work, and using remote sensing data from different platforms, from different different platforms for different applications, looking at, for example, urban or like agro ecosystem or forest ecosystem. So basically apply these geospatial technologies to derive information for whatever applications, I mean environmental applications. So but my second line of research mainly actually is kind of like go a step forward, incorporate this information plus other environmental data and combine with models, combine with either process-based model, like climate model, weather model, or like land surface model, or simply like the data mining model, and to address problems and, for example, look at how much carbon actually a system may lose or acquire after certain so-called disturbance, and something like that. So, but mainly actually I'm going to actually focus on the second part. I mean, if you have been learning statistics, everything here are very straightforward to you. I'm sorry for that, but here I just want to share a few points. And so the reason actually I'm trying to make it simple, that actually a story that happened recently a week ago. And I and two other colleagues are teaching a course on using R to analyze data. And my two colleagues actually try to spend probably 20 minutes to explain to the students what's the difference between standard error and the standard deviation. I mean, they just actually my two colleagues actually why they spend so much time, because even within them they couldn't really agree on what exactly the difference. So somehow that's why. So don't be surprised. You won't be learn nothing new. I just somehow try to share a little bit of my own perspectives on these simple things. So this is somehow the next few minutes probably talking about my own expertise, my own recent research. I use remote sensing data a lot, and specifically the so-called hyperspatial resolution or hyperspectral or hypertemporal resolution remote sensing. For example, image here you saw actually is a Google Earth image, which is pretty high resolution, and you can see the details, and which actually can allow us to really identify the individual object. For example, the buildings, the tree patches, and sometimes even cars. So this can allow us to do the so-called object-based analysis. This is somehow a forefront of like image analysis, from pixel to object. And another very fancy remote sensing technology actually that have been emerging for the past decades is LiDAR. So LiDAR is more or less laser scanning, which actually you not acquire image, but you really acquire the three-dimensional data points, which allow you to see the details of the structure, like 3D information. For me, I'm mainly using LiDAR to look at the canopy, like trees and tree structure. And so another is hyperspectral, which actually you normally have a couple, go beyond a couple of different bands, and to a degree where you have a couple hundreds spectral bands, which actually can give you a very detailed reflection spectrum, which can allow us to, for example, acquire a lot of information about the biogeochemical properties of ecosystem. For example, we care about how much actually, for example, nitrogen in the leaf, how much chlorophyll, and so, or how much phosphorus. And this spectrum actually somehow can allow you to go back to derive this kind of information. And hypertemporal, and so that's definitely important because that gives us a time dimension which allow us to track the change, and track the interaction, and also track the dimension. And the example here is the so-called data from Greece, which is actually a gravity-based satellite using gravity to go back to retrieve the change of the mass in the Earth. And here, the signal represents more or less the water storage in the land system, for example, the soil moisture. So this is one recent example study I just finished, and this is actually somehow capture all the three aspects I mentioned: hyperspectral and hyperspatial and hypertemporal. So this is LiDAR, so it is hyperspatial, and which give us a lot of detailed information, which normally this is a three-dimensional point cloud, which actually capture the distribution of the plant materials, for example, leaf, branch, and bark. And more importantly, for each data point, we also have this spectrum, this hyperspectral information. Actually, that allow us to, from this spectra, go back to look at information. For example, here I'm looking at the leaf water content. And this is also hyperspectral data because here, hypertemporal data because, and for this particular scan, we actually scan every hour for over a day. And so this is actually some quick dirty result. And X here is the hours, and Y here is the height about the ground, about the tree crown base. Color here indicates the leaf water content. And so, for example, here you can see for this tree, you can see the dynamic of the leaf water content over a day. In particular, this brown area indicates the dry water, the leaf become drier during the after probably 12 o'clock. I can see this like a diagonal cycle. So this is pretty relatively new technology, and to my knowledge, there's only one single system can allow you to do hyperspectral LiDAR. This is the system, actually not my system, but actually a system from a collaborator in Finland. So I'll be imagining probably in a couple of decades, you're going to definitely see explosion of this kind of technologies. Not only for looking at trees, probably looking at other things on the Earth. So that's actually one single study. And another study, this is another example to explain the second line of research I'm doing and trying to incorporate this data to answer some questions either related to policy or climate change or like ecosystem dynamics. For example, one model I use a lot is called EPIC. So EPIC is a pretty complicated model, and it's one of the two models used by IPCC to assess food production in the future climate. And so I do actually use this model trying to, for example, analyze the crop production pattern over the next century, and for a few major crop types, for example, corn, soybean, and wheat. And this is somehow the process-based model. And on the other hand, I do actually rely a lot on data mining approach, and by looking at the data itself and trying to infer the pattern. For example, on the right, which actually real crop yield data, and specifically for corn, and over the Wayne County over the past 50 years. And one actually information we are pretty interested in is to see how climate, how this weather variability actually affect this crop productivity. Rather than pursuing this model, a process-based model, here we only actually using data to answer this question. But apparently this kind of like a pretty challenging question. As you can see here, and so the data actually not just contain the climate signal, but there's a lot of variability that actually is driven by other factors. And specifically, you can see the trend. So this is due to the technology advancement. So somehow, in order to take this data, you somehow had to incorporate all these factors and and put this factor into your models and to somehow untangle these relationships. I'm not able to actually kind of like present a result. So this is just actually two examples somehow give you ideas about what type of research I'm pursuing. One, remote sensing based information development. And second, actually apply remote sensing information or climate or environmental data to answer some questions for agro ecosystem and forest ecosystem. So now let's switch to the gear. And so this is somehow the simple point I want to make. And so you can just read it. And so that's straightforward. And so I won't really be able to use my own research story to explain some point, but rather here I really use some very simple, sometimes naive example to explain my point, as you will see pretty soon. So data is important, and without data, I couldn't publish my paper. I believe that's the same thing for you guys. And so, I mean, sometimes even if you want to make a very simple point, and even sometimes really maybe just some very self-evident point, you still need to have done some data to support it, and so actually can go through the peer review. So here are just a few examples. For example, the first one, and so to me, that's definitely a very funny conclusion, but still actually they put money and they put a lot of work and to collect this data to support it. And sometimes, for example, even for some simple point, for example, for this one here, this is actually funding from published in Science, which says the more time a person lives under a democracy, the more likely she or he is to support democracy. So again, it's straightforward, but you somehow have to have data to support it. So this indeed actually from my research, this is actually research I did together with other few people when I was a postdoc a few years ago. And so we are actually, we know people complain the potential impact of hydrofracking. So especially this groundwater and or water from a well. And I mean, people know that, and people know that from their own life. But how we can make this story, how we can make it actually published. And essentially, we actually somehow collect very simple data. So this data actually X here is how far the ground well is from a hydrofracking site. And Y here actually is a methane concentration in our water. So it's not really perfect data, pretty noisy, but somehow it's good enough to tell you a pattern. So basically, the closer your ground well is close to the hydrofracking site, actually, the more likely actually you see the high methane concentration. Apparently, the story shouldn't be that simple because there can be other potential confounding factors behind this data. So, but for make a simple point like this, somehow that should be very positive. So this is another study actually done a few years ago, again, when I was postdoc. So people know actually this natural gas leak is leaking almost everywhere in some mega cities, and have some potential impact on climate or public health. But so we know actually it's leaking, but the question we want to ask how much leakage is there, and how much actually is leaking, and so what is its special pattern. So basically, we somehow using a mobile device and driving around a few cities and making these maps. So this is the data, and this is also the story of that kind of research. And where you can see here, this red lines here are the road we drove, and these green bars here are the leakage we find over these different cities, one Boston and DC and New York. So we know data is important, but so the problem actually, I mean, I do have millions of ideas in my mind. I can actually, I think I can publish, but the problem actually somehow we don't have data. So that's why I emphasize the data is another important component. So the most important thing is not really about data. It's actually about availability of data. How you design your study to acquire data. So this is somehow a very interesting study, again published probably 10 years ago in Science. So trying to explain the so-called out-of-body experiences. I mean, so we all know, probably heard from news or from this novel, normally when you're near death, you can somehow feel this kind of out-of-body experiences. But how we can study that? I mean, a few guys from, I believe it's from Britain actually, they figured out actually pretty smart design. So by using these kind of cameras and so record the back of this participant and send it back to the video here. And so this guy can see his own like a back. At the same time, the scientists actually use a pen or whatever to touch the body. Actually, that somehow creates this so-called out-of-body experiences. So this is actually another two recent study, and so this is the conclusions from these two studies. One saying there's no linkage between marijuana use and IQ decline. Another one actually saying killing predators won't actually help to protect the livestock. Somehow this is counterintuitive. But whether this is true or not, who knows? I mean, still they have data, but many people have data somehow to answer the same question. But the problem because the data is not perfect, and the data couldn't really answer the question itself. Somehow you had to make your own inference or trying to use a model, trying to use different data analysis procedures to make sense of data. So that's why somehow even with the same data, people can arrive to different questions, different answers. So I wouldn't be able to actually go through all these details about these studies. And although I'm pretty familiar with their details, that's not my own study. But this is somehow more or less a study I did when I was postdoc again a couple of years ago. So I think a couple of years ago, there's in a New York Times, there's an article saying to save the planet, don't plant trees. And this is really horrifying. I mean, especially to many climate scientists. And so similarly, and again in 2010, a paper in Science, basically concluding actually desert actually good for climate. Well, in itself, this is a pretty respected research, but again, the problem here, they use some data trying to incorporate either this climate model or either trying including statistical model trying to make sense of that data to reach this conclusion. So they actually somehow have this kind of very novel ideas. But the problem here again is how much sense this make to you or to me is really depending on actually how much you understand the system, or how much you trust your data, and how much actually you trust your model. So one study I did actually trying to tackle the same question, again, rely a lot on data and look at actually how different line of cover may affect the biophysical interaction between the land and the atmosphere. So when people make these conclusions, so they are mainly looking at not just the carbon footprint. We know if we grow trees, it's good for climate because carbon draw down CO2. That's good for climate. But on the other hand, the trees actually have the lower albedo, a little bit darker. So which means it can absorb more solar energy. That actually can be warm the climate. So you can see the picture is not that simple. The picture is somehow pretty complicated. And so in my paper, actually, I didn't really go far away to make this kind of like a conclusion. And the only conclusion I think I made in my paper, actually, if you try to grow trees to actually mitigate the climate change, it's better to grow deciduous trees than growing evergreen trees. That's my message in the paper. So, well, so this is an example probably many of you saw before. And so if you look at this pattern, oh, wow, that's good, that's beautiful, that's cool to be a paper somewhere, maybe, I don't know. But apparently, if you look at the the title here, the black curve here actually is a PhD grade in sociology awarded in US. And the red curve actually is a number of satellites launched worldwide. Apparently, according to our logic, there's simply no connection between these two variables, but can see a very strong connection. And this is the same thing again for two random variables, variables. Divorce rate in Maine and the consumption of margarine actually here in the US. So this actually correlation is pretty strong, almost 0.998 something. So this is a very extreme example, saying actually, but in our data, so normally we don't have this extreme example, but still you can see when you try to make sense of your data, so there's a lot of subtleties there. So there's actually a lot of room and for whatever, for manipulation or for your own interpretation. So anyway, so normally we shouldn't actually just let data to speak for themselves. We have to rely on models. Specifically, if you work on discipline, for example, if you work in climate, definitely you rely a lot on the climate knowledge, the physics. And if you want to work on ecology or work in physiology, you need to rely a lot on these biological theories. But I don't expect you to read this kind of words here, but this is all some modifiers to model. And in particular, I highlight a few of them. For example, physical, statistical, and predictive and explanatory models. So either the t-test, that's a simple statistical procedure we use a lot. So that's also a model, and in a broader sense. So it's hard to give a very exact definition to model. And here is my own version, a very simple one. A model is just actually a simple construct of something, and something can be anything. And normally the best model actually is physical model. For example, we can use a wind tunnel or using this kind of sniffing dog. And so we know a lot of computer scientists, they try to build a very complicated model to do this pattern recognition. But here we try to train a dog and using its biological system actually to build a very smart, this kind of like pattern recognition machine. So this is somehow also can consider as a physical model. So speaking of models, one thing you heard a lot is all models are wrong, but some are useful. Whenever I saw other people mention this in their presentation, I always kind of like get tired of that because I have been hearing this many, many times. I couldn't really recount how many times I've been listening to this. And this is originally actually from George Box, I think from a book. And so this is the context where this quote comes from. And the main message here, actually, I think he tried to want to emphasize not really the second part, but mainly the first part. So basically, saying all models actually are not really the truth, but rather than a simplification or approximation to the real world. So this quote is simple, but many different people have totally different understanding, and they also try to apply this simple principle differently to their research. And one recent article I saw actually is from another professor. His name is Dr. Tarpey something, and he's saying actually, if you try and see model approximations, I mean, by saying something is approximations, we are literally saying, okay, this is not right. So in his point of view, it's probably make no sense or little sense to try to judge whether a model is right or wrong, but rather because they are simply not right at all, because they are simply approximations. And in our daily language, if we see something are some approximations, and logically speaking, we can think that's a right thing. For example, if this is our model, and how many days in a month? 30 days. That's not definitely wrong. But rather, if we are saying, okay, there are probably 30 days in a month, approximately 30 days, this definitely somehow either scientifically right or either like make common sense. So it's not wrong. So similarly for this linear regression here, and so if you're saying, okay, I assume this error here, the epsilon here or the e here, is normal. So at least for all the models I'm using, I'm pretty sure actually definitely it's not model. It's not normal. It's not really Gaussian. But rather, I would like to say, okay, my model here or my error here is approximately Gaussian, approximately normal. So this actually is a more accurate representation or accurate description of my models. So that's why somehow you wouldn't say this is too wrong. So that's why here Dr. Tarpey is saying, actually rather than saying models are wrong, and he's saying actually all models are right, and but most actually are useless. I mean, whether models are wrong or right, actually to us, we didn't care. So it doesn't make actually, we still use the model the way we are using, and so normally I think whether model are right or wrong is really a personal matter. So it's depending on your own perspective, and also important depending on your own knowledge, and depending on how much information you have, and also depending on how much data you have to evaluate and to verify and to improve your models. And so this is the philosophy I applied to my own research, or I personally embrace. I thinking all models are definitely not right or wrong, but I'm thinking all models are useful to some extent. But we can go further to evaluate or verify or quantify the relative usefulness and of the models based on observations, based on data, a posteriori. And here I want to emphasize two words here is relative, another is a posteriori. And by relative here, which means actually we're never going to arrive at the point where we know the truth. And by a posteriori, which means if you will become clear, it will become clear a little bit later. By a posteriori, I mean, I'm basically pursuing a so-called a Bayesian approach, a Bayesian perspective. Because when we're talking about data inference, we have two ways to think about the data. One is the so-called frequentist. Another one is called Bayesian approach. So I'm basically a very strong advocate of Bayesian approach, and I will talk a little bit later at this presentation. So that's my perspective about models. So what is a useful model, or what is the best model? So a very academic answer is it depends. I mean, so indeed that depends. I mean, it's depending on your problems, it's depending on who you are asking. So I like to use some simple example, not really example from research, but using some really example to make this kind of point. So these are 3 models, and for the same person. And so if my purpose is to, for example, and using an image for my ID, or I post for a dating website, or definitely the second one is probably the best. But if you try to, for example, do a pattern recognition, tell me whether is this a human, or whether this is a dog, whether it's a tree or bird, I mean, this is sufficient. I mean, you can tell this is not a dog, not a tree, this is human. So that's sufficient. So that's actually is good enough for that purposes. And actually the one here on the very right, that is a very high resolution image. And this is actually a zoom in to her eye, which actually can see the light, the lighting device, and also the camera in his eye. I mean, let me see. Can you go to this? Well, I don't want to wait, but okay, it's coming. I basically can zoom in actually to see the spatial details, and so it can offer. So I mean, this is not necessarily a good model because first it have really too much spatial details, and that can cause trouble to a lot of data analysis algorithms. But it's good for some purposes. For example, if you try to present this image for a doctor, so that actually can present more information. For example, if you have skin problem, and so actually take that picture can reveal the detail of skin. So this is another example here, and I don't know how many of you know this game mod, and so this is a game actually I have been playing when I was a college student, but nowadays I think nobody plays this, but rather than a Pokemon Go. And so, I mean, speaking these 2 models, and I mean, if you saying okay, try to make a computer model to make money, and or to like attract these users, I mean, this could be the one to go. But for me, I personally like this model because this is the model I have been used a lot, and I play probably, I don't know, 5 or 6 years. And so this is actually the model to help me to learn English word. And you had to type in this like word, like for example here, kill worm, and then it's going to try to wait for a few seconds, and you're going to see, oh, worm killed. So that's why if you think about which model is good to train your imagination, I would say this one. While you're waiting for that worm to be killed, actually in your mind, in a few seconds, you can actually imagine what exactly happened to that worm, and not really looking at a picture, but actually create your own imaginations. So with that being said, actually here, it's really depending on the users. Apparently here, I also emphasize here, I like this better. I think this is better model. So again, so here, the personal belief is important things when we're dealing with models or when we're dealing with scientific research. Again, that actually along the line of the so-called the Bayesian paradigm. This is another example here, and so this is actually the instructions from the Courtney Hall here, where the SNR is, and to here. These are 4 different models, And I mean, speaking about their utilities, they are somehow are all equal. This exactly I should tell you how to get from one place to another place. In particular here, I have a model here, and so
向北继续前行，科菲路走向木质的海丝路，左转到木质。
Well, I believe this part makes no sense to most of you, but indeed, actually, this is the model makes much sense to me. Makes sense to me. I think it makes sense to my students. So this is not in English. This is Chinese. So you can see here, to me, all these models are equal, but to you, this is a very bad model. This makes no sense. So again here, the model depending on the user, depending on the model itself or themselves. So come to scientific applications, and so what is the purpose of using models? And people have been debating for the past century, and in many different disciplines. And recently, there's a lot of debate in the social science arena. And eventually, they arrive at these simple conclusions. So there are two major scientific goals you try to meet when you try to use models, and either to explain or to predict. So these are somehow totally different scientific goals. And to predict means you try to make prediction based on the information you have. For example, when you go to Target and you do your shopping and you actually check out, and then actually they can give you a coupon for something. Actually, they actually predict what coupon you may use based on your shopping list. That's actually a prediction. But for most of us, we care about the theory. We care about this causality. So that's actually mainly speaking of explanations. So normally we are thinking if a model have more explanatory power, we're thinking it's going to be a better predictive models. But in general, that's not the case. So basically here, the explanatory power and this predictive power somehow are two different aspects. And so again, I come to this example here. This is again a very extreme example. If you are seeing whether this is a good explanatory model or not, definitely not. This is totally a very bad model in terms of explanation power. But it's very strong, almost a perfect predictive models. For example, if somehow you miss the data for 2004 for the divorce rate in Maine, and so rather than spending probably, I don't know, maybe a couple $100 or even couple $1,000 to reanalyze data, you can actually build a simple model, try to predict this number based on this consumption of margarine data, so almost perfectly. So in other words, this model is very bad, or even probably the worst explanatory model you can think of, but it's probably the best predictive model you can find. So this is another example here, and the two x here, y is a predictive power, and y here, x here is a explanatory power. And this is actually our two extreme example. And here we have the evolutionary theory. That is actually the model that can explain the evolution of human or evolution of the Earth. But we know that's actually somehow, at least to me, that's really a strong model with good explanation power, but it has no predictive power at all. If you try to predict how human society looks like within the next century or whatever, there's nothing to do actually from this model. But in contrast here, we have a model actually that people use for 1,000 years. trying to look at stars and consider Earth as center for navigation. I mean, if you're speaking of Earth as the center, that's definitely not right. Because we know actually somehow the universe is not like that. But people have been using that for 1,000 years. We actually can use that for navigation. It's serving us pretty well. And so that is pretty strong predictive models. So let me see how much time I have. Let's see here. All right. I think actually I already run over time, and so I'll kind of quickly go over a few points, and hopefully I can finish everything before like 1 o'clock. Yeah. So speaking about actually models, I'm here. We are talking about statistics and statistical models, and some people confuse what's the difference between probability and statistics. And actually, that's actually the two sides of a coin, and they are somehow refer to the same thing, but on the two sides, they are actually somehow an inverse problem. And normally, the probability is from the parameter to the data, but for statistics, actually, it's kind of go from data to your parameters. So that's actually two different process. I mean, apparently not all people actually hold this view, but at least a couple, like statisticians, for example, Dr. Percy Diaconsi and a professor from Stanford, and Dr. Jeff Hart, and so they actually voice this view very expressively. So, in other words, in order to actually to build a statistical model or apply statistics, you had to have a probability model underlying. Sometimes I saw a lot of equations like this in some publications, saying, okay, I'm fitting a linear regression model. So by putting an equation like this is not an equation model. This is not linear regression. This is not a statistical model. So this is just an equation, because there's no randomness, there's no probability. You somehow have to put this error here, which makes it a regression model, make it statistical models. But this model as itself, you couldn't fit it, and you had to somehow tell more information about what probability model you have. In particular here, I'm saying my error here is not Gaussian distribution with zero mean, and with the standard deviation is sigma squared. So this is actually a statistical model you can work on, you can fit. Apparently here, really to run statistics or to draw inference, the key here is randomness. So normally you wouldn't really think that too much, and but for some people they are thinking, where the randomness come from? So I mean, there's many different views depending on the problem at hand, but in many cases, I think the randomness is not really pure randomness, but rather it's really somehow represent of the shortage of information you have on your own. So this is actually a view from this novel saying randomness is fundamentally incomplete information. And to me, actually, that makes a lot of sense. And for example, when I try to build models, I assume all kinds of errors, all kinds of random variables. But whether that makes sense or not, that's really depending on actually your own knowledge. For example, when you're saying, okay, I can create randomness by tossing a coin, I mean, but that makes sense. But on the other hand, so for some people, and for example, for a magician, they can actually control control every time whether it's a head or tail. I mean, if either not for a magician, if you give it initial conditions of the cone, the speed, and you give the conditions of the air or the wind or temperature, it can exactly predict actually whether it's cone, whether it's head and tail. So you call it randomness simply because you don't have this initial information to predict its destiny. So I mean that's probably a simple example to explain here randomness is simply a shortage of information. So this is actually my view, and so randomness actually again is because our inability to acquire this perfect information, or our lack of desire to acquire this information. So speaking of probability, there are actually two major schools and two cultures, and probably you already heard this a lot from other colleagues. One is so-called Frankfurtist, another called Bayesian, and they have totally different explanation of what is a probability. But for Frankfurtist, just like we're talking about coin tossing, I mean you can see or define probability by tossing coin a million times or a few hundred times, and counted how many times is on tail and on head. So that's actually the frequentist explanation. But on the other hand, and so for something we couldn't really define this probability in a logical way. For example, if you are seeing the probability of raining tomorrow, can you do this experiment 100 times and to see how many tomorrows will have raining or how many tomorrows will not raining? So that's not really makes sense sometimes, and so that's why somehow another school of statisticians actually they try to pursue this so-called Bayesian perspective, and trying to saying, okay, probability is nothing, just your personal belief. I mean, for example, again, coming to the weather example. For example, if you are a meteorologist, you have knowledge about this weather. If you saying, okay, predict the weather for tomorrow, because you already are trained, so definitely you have better prediction than other. You may see, okay, the probability of raining tomorrow will be 90%. So that's your belief. But for us, and we all just say, okay, it's 50-50. So both these probabilities are 90%, 50, that makes sense. And I mean, to this individual people. So that's somehow this Bayesian perspective, how you treat probabilities. So this actually caused a lot of problems, lots of concerns. And people have been debating about this for probably, I don't know, maybe 100 years, and about whether which is more sense or not in terms their scientific use. And in particular here, I want to emphasize, so this is very important. I mean, normally I ask people to tell me, so how to interpret the confidence interval. I mean, so that's actually totally depending on your perspectives. If you try to take this so-called frequentist view, which actually is most the view you actually adopt from your statistical class, although the professor maybe not really tell you that, but that's actually the view normally we are trained of. And so in this frequentist perspective, and this confidence interval is nothing but just actually a way to express that how much time your confidence interval will contain the true value if you try to repeat this experiment. So two keywords here is you have to repeat this experiment. Another word here, the true value. Normally for frequentist point of view, you must have a true value for your parameters. But for Bayesian, there is no true value at all. And all information is encoded as a probability distribution or as a random variable. And normally it's represent the information as a creditable interval. So this may be a little bit confusing, but I do have a figure to explain this better 2 slides later. So let me explain the Bayesian, the frequentist versus the Bayesian a little bit more here. So this is a really typical linear regression models. And for us, normally we assume the this A and B, and also this sigma square here. And we assume actually they are constant, they are fixed, and there's some value for them. But we don't know them, but they are there. They are fixed values. In other words, the only random variable we have here is y and epsilon. So these are the 2 random variables. So this is somehow the frequentist view. But for this Bayesian approach, and here you somehow assume these parameters are also random. By random, which means there are no true value at all. So you have to use probability to describe them. And also in this model, almost every variable here are random variables. For example, y, a, and b, and epsilon, and sigma square, these are all random variables. So normally you heard something like, there is a 95% chance that the true value is in the confidence interval. So is this a true statement or not? So actually, if you try to be serious, so this statement is not right, either in the Bayesian perspective or in the frequentist perspective. So like I said, in Bayesian perspective, there's no true value at all. All the information are encoded in probability distribution or random variables. And this circle here, this is my credible interval. This is just a 2-dimensional confidence interval or credible interval. And this is my value, and this is my estimate. So the Bayesian interpretation of this confidence actually is that saying your parameter have 95% chance within your credible interval. And here actually your credible interval actually fixed, but random actually, the variable, the parameter actually is changing. Compared to the frequentist perspective, which probably your professor emphasizes this a lot. So normally the true value is there. This is a true value. We never know what it is. And the confidence interval actually you derive is this one here. So by 95% of chance actually, or by 95% confidence interval, so which means if you repeat the experiment 100 times, you get 100 of confidence interval. And probably on average, 95 of this confidence interval cover your true value. But for the particular interval you get after you're doing PhD, spend a couple of years, and you probably only get one interval. So you never know whether that interval contains your true value or not. So that's the difference. All right, I think I will get to just jump to the very end. I have a few more slides. I don't want to somehow run over too much. And here, okay. So I'll just quickly show this kind of like a graph here. For example, here for the traditional frequency view, we normally take this called a maximum likelihood estimation. And for example, if we try to estimate the length of my seminar or the length of seminar for this particular, when I see this number, I feel so bad. I mean, definitely not 45 or this per almost an hour. So if you try to estimate the mean length of seminar based on the previous seminar length, I mean, if you try to build a model, and this is actually a likelihood model. If you have only one observation, but you have two observations. You time your probabilities, you get this red stuff. This is actually your likelihood. If you have more points, more data, your likelihood function will get narrower and narrower. So actually, the so-called maximum likelihood estimation will be the value actually here corresponding to this peak. This is a so-called maximum likelihood estimation. But for Bayesian, actually, it's always use this so-called Bayes formula, where, so this is the likelihood you just saw in the last slide, and this is the prior. So this is actually where you express your personal belief. And for example, here, this is the likelihood of the mean time, which we saw in the last slide. And here actually is your personal belief and of how long this seminar will be. And then you can do this multiplication, and then you actually get this green curve here. So this is actually the posterior probability distribution. All our information are represented by this green bar here, or green probability distribution. So in that case, your information not really upon a single value, but really a distribution. All right, I'll stop here. But I do have a few take-home messages here. I think the main thing here actually is for somehow to let you learn me, and so that's actually for me the main purpose of this presentation. You notice here somehow I present two models of this key point. So Kai and Kaiguang, and so these two models are somehow roughly the same, but they're different. And so I think to most of you, probably the first one is better because that has Kai maybe a little bit easier to remember, but definitely this is more or less a true model according to Marx's perspective. And so one thing I emphasize a lot actually, when you're trying to use models or doing statistical analysis, it's always good to ask you the question, so whether your purpose is to predict or explain. I mean, normally, we doing research from different perspectives, using different technologies, addressing totally different questions. I mean, your whole PhD dissertation maybe not about data, maybe not about a model, but there should be something on using model, using statistics to answer questions. And in that small component, I think it's good to somehow to really understand what is the real purposes. And so the two views, the frequentist versus Bayesian approach. And so normally the Bayesian approach become popular, which I don't have time to task today, is because it's more flexible and you can incorporate more information. And for example, speaking about like environmental studies, environmental data, we normally have data from different sources, different resolutions, different nature, and different temporal resolution. And so this data are really complex, and normally at multiple levels. But if you try to build a model to draw information and draw scientific conclusion from that, and trying to solve using the maximum likelihood approach, it's very complicated, and so sometimes it's not impossible to address. But for Bayesian approach, actually, the good thing here, Bayesian not normally is not really purely mathematical, but rather actually is more computational, which allow you to incorporate this complexity by using computer to draw conclusions. So that's why it can handle more complexities. All right, I'll stop here, and welcome questions if you have.